So what I wanted to do is I wanted to make an example problem using what we've learned from circuits in series. I find it pretty important to be able to show an example of how to do this, just to make sure that everyone's on the right page, as I haven't done with my previous videos. So what I have here is I have a circuit. There's a voltage of 36 volts here. And I have two resistors, one at 3 ohm and one at 6 ohm. What I want to do is I want to determine the amount of current that's traveling through the 3 ohm resistor. Now the question you first have to ask yourself, is the current between the 3 ohm resistor and the 6 ohm resistor going to be any different? Are there, because of less resistance, it would seem to me that there'd be less, or there'd be more current going through that resistor, where the 6 ohm with higher resistance should have less current. I mean, that seems to be our definition of resistance, is this impedance to motion of charge. The truth of the matter is, though, that if that was the case, if the 3 ohm was letting through more current than the 6 ohm, then you'd have a buildup of current in here, in the region in between the 3 and the 6. Now, that doesn't happen. I mean, think about the ramifications of something like that happening. If this was to let through 2 ohms or 2 amps of current, and this was only letting through 1, that means that 1 amp or 1 coulomb is being added to this region, this piece of wire, for every second. It's a lot. Now, even if that's not, even if it wasn't a total of 1 amp, but maybe some microamps or some milliamps, you're still building up charge. And that charge is eventually just, you're not going to have anything left other than charge in there. So it just doesn't happen. As a matter of fact, as the circuit is built, as it's finished, and as the switch is thrown, and the battery starts sending charge through, you can sort of think of the system as, or the battery as, knowing what's in front of it. It sees the path in front of it, in a sense. I mean, obviously it doesn't, and knows that it can only release a certain amount of charge without it building up somewhere. Okay? So what we need to do is we need to determine what the current is going through the entire circuit. And knowing that the current through here and the current through here are identical, that would mean that the current going through the entire circuit would be equal to the current going through the 3 ohm. So, how do I determine that current? Ohm's law. Let's start with that. So Ohm's law is V is equal to IR. Okay? The total voltage is 36. The total current is what we're looking for, and resistance. Now, we don't know the total resistance, which is what we really need to know to determine what the current is through the entire circuit. So I have to come up with a way of calculating the total resistance. Now, in the previous video, I said in series, resistors are additive. Okay? So that means that the total resistance is 3 ohms plus 6 ohms, or 9 ohms of resistance. Okay? So that means that this term turns into 9 ohms. So rewrite it as 36 volts is equal to I times 9 ohms. Now, solving for I, all I'm going to do is take 36 and divide it by 9, and I'm left with my current equal 4 amps. Okay? So that means at any point in this simple series circuit, the current is 4 amps. Anywhere. 4 amps. Okay? So the current going through the 3 ohm resistor is 4 amps. Okay? It's not some other value of that. It's just 4 amps. Cool? Now the next thing I wanted to do is I'm going to put in a couple of points. I have a point here, I'm going to call A. I have a point here, I'm going to call B. And a point here, I'm going to call C. Now, another thing you need to know about resistors is that resistors consume potential. That's That's their primary function in life, is to consume potential. And now, why would they do that? I mean, why would we put resistors in a circuit in order to consume potential? I mean, you put a potential in here, and there's charges flowing around. So basically, we have energy. So the job of that resistor is to consume that energy that's floating around. Why? Well, it's not that it destroys the energy. We've looked at systems before, especially dealing with conservation of energy, and energy isn't getting destroyed, it's being transformed. Okay, so the energy is being transformed as it goes through the resistor. Now, what form of energy? Thermal. Primarily, I mean almost entirely. I can't think of another way in which energy goes through a resistor that's not being transformed into thermal energy. Why is that beneficial? I mean, we talk about thermal energy being as useless energy. Well, it's beneficial in the case of a light. You know, when you look at a simple incandescent light bulb, the filament is nothing more than a resistor. So that resistor takes that energy that's going through the system, and it's converting that energy into heat, into thermal energy, generating heat, generating light. And you know, that's only one example. You have other resistors doing other things for you. Let's say you have a circuit that is relatively fragile, and you don't want 36 volts through a particular part of that circuit. Well, you put a series of resistors in front of it, and you can lower that potential so that instead of 36 volts, or in the case of a wall outlet, 120 volts, it's only experiencing maybe 10 or 5. Okay? So those are things that are all kind of important and why we use resistors in circuits. So what I want to do, calculate the consumption of my potential as it goes from point A to point B. Now when we talk about potentials, we're talking about the differences between one point to another point. We don't talk about the potential at the resistor. We talk about the potential across the resistor, A to B. Okay? So we're looking for V. And what was the current that was going through that resistor? What was the current there? Well, it's 4 ohms, or 4 amps, sorry, not ohms. 4 amps is 4 through the entire circuit. So it's 4 amps. And now, we're not concerning ourselves with the entire circuit, we're only concerning ourselves with one portion of the circuit. So what's the resistance for that one portion of the circuit? 3 amps. 3 ohms. Okay? So that means that my potential drop is 12 volts. That means that after it goes from point A to point B, my potential will drop by 12. So if I started off at 36, I've now dropped by 12, so now I'm at 24. I have 24 volts coming across the 6 ohm resistor. Okay? Cool? So what I want to do is I want to calculate how much voltage is consumed in that 6 ohm resistor. Well, back to the original idea. V equals, well, my amps are still the same. It's still 4 amps. My resistance is 6. 4 times 6 is equal to 24. 24 volts are being consumed. I get a drop of 24 volts from B to C. So from A to C, I have a total of 36 volts that are being consumed. They're dropped as it goes across that circuit. Okay? And that's an important note. That's something you need to realize, is that when you have a battery in there, and it does create a potential, that potential is consumed. As it's going through that circuit, everything is consuming that potential. On the flip side, if you think about building something and you're plugging in a power supply that's not supposed to go into that component, you know, you take a 120 and you plug it into a flashlight that's only supposed to be taking 6. Okay? What ends up happening is that resistors in that flashlight, aka the light bulb, has to burn off 120 when it was originally built to only handle 10. So the problem with doing something like that is that you're burning off that tremendous amount of potential in something that's really not designed to do that. That's why your light bulbs burn out really, really quick in that sort of situation. It's also important to note that your light fixtures are rated for a particular voltage. In a sense, they're rated for a particular potential consumption. If you put in the wrong light bulb into that socket, you may end up shortening the life expectancy of that light bulb. Now, the new fluorescent light bulbs are underrated. They only require so much wattage, more or less. I mean, their potential consumption is less than the traditional incandescent. So they don't need as much. They actually lower that potential that they need. Okay? Anyway, off on a tangent. That's a basic problem using this idea of series and Ohm's law.